Welcome to this lecture series in general topology. In this lecture, we'll discuss the notion of a basis of sets. This lecture will not leverage on any general topological concepts. It can be discussed, or it could be taken as an independent lecture in some sense, but it is very important for what comes next. All we need to know roughly is the standard inner product on Rn and the Cauchy-Schwarz inequality. I will recall it when the time comes, but I'm pretty sure you already know about them. And now let us proceed. Here are some problems for practice. And now let us get started. So we will define what is meant by a basis of sets. Fix any non-empty set X and let B be a collection of subsets of X. Okay? So we say script B is a basis on X if, so before I say what the conditions are, let me emphasize that this has nothing to do with linear algebra. It is just an unfortunate clash of terminology. When we have a vector space, a certain list of vectors is called a basis. Well, the definition is that it should be a spanning list as well as the vectors in it should be linearly independent. Here the word basis is used, but in a completely different light, or it has a completely different meaning, right? So let's not get confused about that at all. So we say B is a basis on X if two things. The union of all the things in script B is the entire set X, and second one is a little interesting. So if B1 and B2 in B are such that, or if B1 and B2 are chosen in B, and suppose there is a point, and suppose we choose a point in their intersection, well, they may not intersect. I mean, if you choose two elements from script B, they may not intersect at all. But if they do intersect and you choose a point in their intersection, then let me draw a figure. So this is, let's say, B1 and that is B2. And there is this point X. So then what we are demanding is that there is some element B in script B which is contained in the intersection. So then there is B in script B such that X is in B and B is contained in the intersection of B1 and B2. So whenever two elements in script B intersect and we choose a point in the intersection, we can always find some element in script B which contains the point X and is contained in the intersection. I don't know how to say it in words in any less detail than already written. You can kind of say that there is some sort of an infinite divisibility condition here, right? Whenever you have intersecting elements, you can further see the intersection as some union of things here. That's exactly what it says, in fact. So in other words, the intersection of any two elements here can be written as the union of elements here. That's exactly what this condition is. Okay. Unclear why such an object is useful to us, why do we care about it, and in this lecture it will remain unclear. In the next lecture we'll see the use for it. Why at all bother about such a thing? Let's just take it on faith that it will be useful, and with an open mind, just take this as a game for now. We will prove certain things. We will create some bases on the Euclidean spaces and other things. And let's just see where it goes. So let's see some examples. Let X be any set. And let script B be equal to the collection of all the singletons. So then clearly this is a basis. Okay. Well, why is the first condition true? Of course, if you take the union of all the singletons, you recover the entire thing. And the second condition is somewhat vacuously true. If you choose two elements in this thing which have a non-empty intersection, then since each element here is a singleton, you are forced to choose B1 and B2 to be same. The only way two things here intersect is that they are the same. And then how do you find something? How do you find this thing once you have found B1 and B2 which intersect? Well, this is equal to either of those because they are equal anyway. So if let's say B1 is equal to x naught, which is also same as B2, then they have non-empty intersection, and then you just choose B as again this set. So this condition will also be satisfied. We are not demanding that this be some strict containment or anything. This is just a containment. Alright, so this is a basis. Let's see a little bit more interesting example. This time let x be this set, the natural numbers along with a special symbol called infinity. Forget about the topology on it that we discussed because this lecture will not be concerned with any topology whatsoever. So then, or let script b be this thing. You collect all the natural numbers in singletons and you also collect the tails. Let me recall what are these tails. So ln is all the naturals which are at least n along with the symbol infinity. Okay? So we have seen this many times. So then this guy is a basis on x. Right? And this one should just check for oneself. Very simple exercise. Okay. Lastly, a very nice thing. I mean, it's very easy, but nice. So let B be the collection of all the open intervals in the reals. Then this is a basis on R. Why is that? The first condition I'll leave to you to check. Well, the entire set of real numbers is an open interval, in fact, because this is an open interval, and this is nothing but all of real numbers. This is trivially satisfied. What about the second condition? Let me draw a picture. So we have all the real numbers, and let's say we have two intervals which intersect. So here is an interval. I'll draw it in a more emphatic manner this way. And we have another interval. And we choose suppose somebody has chosen a point in the intersection. Then it should be visually clear that there is some interval that sits inside the intersection and contains the chosen point. So that's the reason. Okay? And you can formally write this. I encourage you to formally write this down if this is not completely clear. Alright, so we have seen three examples of bases. The plural for basis is bases. Okay. Now we'll construct bases on Euclidean spaces. So, recall our two-dimensional Euclidean space R2. So for 2 points A and B, A and B in R2, we define the Euclidean distance between them as this quantity, Well, we already know what is the motivation behind this. A1 minus B1, or the absolute value of it, is this length. Draw this vertical line here and draw this horizontal line there. So the length of this horizontal segment is A1 minus B1. The length of this vertical segment is A2 minus B2, in the absolute value, of course. And then the length of this thing is, by Pythagoras theorem, this entity. So that's why we define the distance that way. So this is motivated by the Pythagoras theorem. You've surely seen this in high school. And the 2 here refers to the 2 there, not to the dimension. I mean, this is R2, so there is a 2 here, but this 2 is not referring to the 2 there. This 2 is referring to 2 here. Okay, so this is the Euclidean distance between A and B. And here is a fact, which again, surely you know from high school or basic geometry, which says that if A, B, and C are 3 points, then the distance between A and C is at most the sum of the distances between A and B and C. And the geometric motivation of it should be amply clear. So let's say here we have a point C. All this is saying is that this distance is at most this distance plus that distance. So to reach from A to C, if you take a detour, if you visit another city in between, you will be spending more fuel. That's the verbal or colloquial way of expressing it. You should prove it by using the formula. That's the only way to prove it. Okay, so I leave the proof of it as an exercise, but I am sure you have seen it earlier. Okay, now we define balls. So for a point A in R2 and a real number greater than 0, define what? Define this object. You have the point A. Collect all the points in R2 which are at a distance less than R from A. So I have made these things dotted. The dotted things are the points which are at a distance exactly R2. That forms a circle. But we are not collecting them. We are collecting the points which are inside the circle, meaning those points whose distance from A is strictly less than R. So we define the ball coming from the Euclidean distance with center A and radius R as those points in R2 such that their Euclidean distance with A, maybe I'll write an X, distance with A is strictly less than R. So the picture is very important. All of this writing is important for expressing the proofs. In order to be rigorous, we need to be able to write these things, and one should be conversant with both the intuition and the formulas, and one should be able to correlate the intuition with the formulas. Let's not lean on one side too heavily. One should be balanced. So this geometric figure, it's a very simple object, so it is not intuitively challenging. But if you want to express it formally, this is the way to express it. Okay, and what we are going to show is that if you collect all the balls, so this is the collection of all the balls of all the possible radii. So you vary over all points and vary over all radii and collect all the corresponding balls. That collection we'll show is a basis on R2. You should in fact take this as an exercise before you look at all the things that follow. Okay, so this is our first order of business. All right. So first we will show a lemma. Fix a point in R2 and fix some positive real. And let A be a point in the ball of radius R around X. Here is a figure. Oops, what did I do? So we have this ball of radius R around X, and A is a point inside it, then there is a t greater than 0 such that the ball of radius t around A is contained in the ball around X that we have. So it's saying something very simple. All it is saying is that if you take a point inside the ball, you can find a small ball around A which is contained in the big ball. Intuitively, this is very, very simple. And it is important that you take A inside in this ball. If you take A at a distance r, exactly r from X, then you cannot make this statement, because no ball of whatever small radius you take around a point on the boundary, this entire thing is never going to land fully inside the ball around X. So if you take a point inside the ball, then there is a small enough radius such that if you make the ball of that radius around A, you will see that this ball is contained in the original ball. Okay, the proof is very, very simple. So let, or just define, before we get there. So let's say the distance between A and X is something. D be the distance between A and X, and let T be equal to R minus T. In the picture, this much is D, and that much is R minus T. Okay, and we claim that the ball of radius T, with T defined as R minus D, is indeed contained in the original ball. Again, intuitively it's very clear, because what are we doing? We are making this ball around A, and the boundaries intersect. The boundary of this ball intersects with the boundary of that ball, but we are not concerned with the boundary. Right? We are not concerned with the boundary. So this containment is what we are going to show. And if this makes you a little bit uncomfortable, you can just take T as half of that. Doesn't matter. Okay, so let's see why. So to show that, we will just pick a point arbitrarily in this ball around A. Let P be chosen in this ball around A. Want to show that P is here. So then the distance between P and X, let me write X and P. By triangle inequality, at most the distance between X and A and the distance between A and P. So in pictures, right, so this thing is that ball, and if you choose a point P here, then all we are saying is that this plus that exceeds or is at least that much. That's what that equation reads. That implies this is at most D plus, because this was defined to be D. And what is that? That is at most, in fact, strictly less than R minus T. Distance between A and P is strictly less than R minus D, because P lies in this ball. Right? So I can, in fact, write a strict inequality with, here I can write R minus T, and that implies that this is less than R, which means P is in this ball. Right? So we started with an arbitrary point in the smaller ball, or rather this ball, and showed that it is in the original ball, and therefore this containment is proven. The existence of such a T is proven. In fact, we can write down the best t that works, in fact, this is the best t. If you take any bigger t, you will be in trouble. Okay. So let's move on. So this time we have 2 points. X and Y are 2 points in R2, and R and S are 2 positive reals. And let A be in the intersection of the 2 balls. Radius R ball around X and radius S ball around Y. A is chosen like that, and let me show you a figure. Yeah, so A is here. So then what do we want to show? We want to show that there is some positive integer t, there is some positive real t, such that this small ball is contained in the intersection of the original balls. So intuitively, we are saying that there is some small enough t such that if you make the ball of radius t, it will be simultaneously contained in the ball around X and the ball around Y. And that should be clear just by the picture. And the proof is immediate from the previous proposition. So we know by the previous proposition that there exists T1 such that the ball of radius T1 around A is contained in the ball of radius R around X. There is some T1 which does that, and there exists a positive T2 such that this containment holds. There is some T2 such that the ball of radius T2 around A is contained in this ball. And now let's take T to be the smaller one amongst T1 and T2. So then the ball of radius T around A is of course contained in both these balls. It's contained in the ball of radius T1 around A, and it's also contained in the ball of radius T2 around A. Right? These two containments are trivial because T is less than, or rather T is at most T1 and T is at most T2 by definition of T. So these two containments are clear, and since this was already there above, we see that this guy is contained there and at the same time contained here, and that's it. Therefore, this is contained in the intersection. So we have proven this lemma, and from here it is clear that the collection of all the balls in R2 is a basis on R2, because the union of all the balls is clearly all of R2. That's not a problem. You take the ball of radius 1 around every point and that will cover all of R2. But now this proposition established the second property required by a basis. So I don't know if I've written it in any way. Yeah, so I haven't written it separately as a lemma, but this shows that the set of all the balls is a basis on R2. Set of all the balls under this Euclidean distance. Okay. Okay, so now we will see another basis on R2. So let A and B be 2 points in R2. We define a new notion of distance between them. Define the infinity distance, or I don't know how to say it. But anyway, the definition is the max of these two numbers. Right? And you can take a moment to think about it. At the same time, we define for a point in R2 and a real number, define the infinity ball, or I don't know the standard name. This is equal to all the points in R2 whose infinity distance from A is less than R. So let's try to understand this guy in terms of these balls. And here is a picture. So suppose A were the origin. It's best to understand in terms of the origin. So this is the origin. What does this look like? Ball, the infinity ball around the origin of radius 1. So by definition, it is all those x's for which mod x1 and mod x2, the maximum of them is less than 1. So clearly, if you make this 45-degree line, then all the points which are before the line x equals 1. So this is the line x equals 1. And let us also make this 45-degree line. All the points here in this region, they are lying inside this ball, because the x2th coordinate absolute value will be less than 1 inside this region, and the x1th coordinate also has that property. So all of those points will be there, and if you just kind of complete the figure, you will see it is a square. Even though it is a square, we call it the infinity ball. Right? Okay. So make sure you understand why this is the shape of this guy, meaning of the infinity ball of radius 1 around 0. Why does it look like that? So just to be very clear, this point on the boundary would be 1, 1. This would be 1, 0, and so on. Okay, I'll not label anymore. So this is a new notion of distance. I think this is also called the taxi cab distance. Doesn't matter. And I want you to prove as an exercise that the triangle inequality continues to hold. Very simple exercise. And if you collect all the infinity balls, or you vary over all points in R2 and all real numbers, and you collect all the corresponding infinity balls, that thing also forms a basis on R2. So just exactly what we did for the Euclidean distance, you can do it for the infinity distance. Instead of circles, you will see squares. That's all. Okay, so now let's move on. So yeah, so this is another basis on R2. In principle, not in principle, I mean this is a different basis on R2. Okay. But perhaps we should see at least some connection between the infinity distance and the Euclidean distance. So here is our lemma. If you know the Euclidean distance between 2 points, you can estimate the infinity distance, or conversely, if you know the infinity distance, you can estimate the Euclidean distance. It will satisfy this inequality. Okay, so let's prove this. So let's first prove this side. So say this is equal to D. That is the maximum amongst these two is equal to D. Then if we take the squares, that thing will be at most D square plus D square, because this is at most D, or rather its absolute value is at most D, so its square is at most D square. Same for that guy. So we have that, and therefore the square of the Euclidean distance between x and y is at most 2D square, and we get this is at most root 2D, which by definition was that thing. Actually, we have proven this guy first. I thought I was proving this guy, but I ended up proving this guy. Okay. So we established that. Now, what about that guy? So, yeah. So for the other direction, we have d2x comma y is, this is square root. And that is at least root d square. Because at least one of these two things in the absolute value is equal to d. Since the max of these two things is equal to d, at least one of these two things is equal to d. Both of them can be d, but at least one of these two things in the absolute value is d, and therefore we have this inequality which is equal to d, which is by definition that. So this thing is at least that thing, and we have proven this part also. So it's a very simple lemma. I'll show you a picture which shows this as a diagram, but yeah, so in fact I'll show it right now. Here is this picture which is exactly in some sense capturing that, but the way to understand it is via this containment. So fix a point in R2 and some real number, then the infinity ball of this radius is contained in the infinity ball of radius R, is contained in the Euclidean ball of radius R, is contained in the infinity ball of radius R. So this thing is that guy, x is in the center. Then here we have that guy, and then the outer one. So this is exactly that. There is no difference between the two statements. So I'll leave the proof of this as an exercise. Just use this to prove that. And this can be geometrically understood very easily just by considering this figure. So please make sure you are able to correlate between, this textual thing and the diagrammatic thing. Okay. And now we can generalize everything to Rn. So the rest of most of things, the most of the rest of the things will be exercises. So fix 2 points in Rn. We can define the Euclidean distance between them as so this is the definition, and the infinity distance as the maximum of these things. And you should visualize these things in 3D, try to do them, or maybe try to visualize the balls. So now once you've defined the distances, you can also define the balls. Maybe I'll do that in the next slide, but for now, here is an exercise. Prove the triangle inequality for both of them. What does it say? It says that. Yeah, so let me know. I'll give the proof of the triangle inequality for the Euclidean distance, and I will leave the proof of the triangle inequality for this as an exercise. Right? So let me prove it for the Euclidean distance. Right. So we will be leveraging some facts from linear algebra. So let W be equal to x minus z, U as x minus y, and V as y minus z. So then W is U plus V. Okay. So what we want to show, yeah, I'm only proving this one. I'm only proving that one. And what we want to show is that this is less than equal to that. Where recall, what is this notation? What is this notation? You must have seen this in linear algebra, but let me recall. So when we write this, we mean the distance between origin and x, right? In linear algebra, we call this the norm of x, because this is nothing but This is nothing but the square root of x inner product x, where this is the standard inner product. Recall the standard inner product. If you take two vectors x and y in Rn, this is defined as this quantity. Right. So with all of that, we just want to show this because what is u plus v? U plus v is, what is u plus v? U plus v is x minus z, and norm of x minus z is same as that thing. Norm of x minus y is that, and norm of y minus z is that. So this equation is same as that equation. Let me write down the main thing that I'm using. I'm just using that. This is nothing but the norm of x minus y. Under this definition, this is nothing but norm of x minus y. Okay, so this equation is what we want to prove, and this will be done by a small application of Cauchy-Schwarz. So we have the square of this guy is, I'll write directly. Surely, if you know your linear algebra, you immediately see this. But if not, just use the definition. Just put u plus v in place of x and u plus v in place of x and expand. You will see that. And now by Cauchy-Schwarz, this thing is at most norm u times norm v. So this is at most. That's exactly the statement of Cauchy-Schwarz, that this inner product is at most this times that. There's a geometric reason for it, but let's not get into that. So what is the right hand side now? This is equal to norm u plus norm v whole square, and we are done, because the square of this is at most the square of that. You take square roots on both sides, you will see this equation or inequation, and that proves the first part. The second is an exercise, and I will formally state it in the next page. So lastly, we define the balls. So for A in Rn and a positive real, define the ball of radius r around A as the collection of all the points in Rn whose distance, Euclidean distance from A is less than r. Right? So this is the Euclidean ball of radius r around A, and similarly you can define the infinity ball. And I've drawn something here which is supposed to denote this guy, but of course there is an n here and the figure is two-dimensional, but this is the best we can do. When we want to visualize, this is the best we can do, or you can imagine in your mind a three-dimensional ball, but anything bigger than 3 is not amenable to visualization. So we just think in these terms and argue formally. When we argue, we write a rigorous proper proof, but this is a very nice thinking tool. Similarly, for this, we just draw this square and be happy. That's the way to think about it. Okay, and now we have a bunch of exercises. Very important that you do all of them. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.